right, diving right in. Today we're looking at a super interesting area where cutting-edge hardware meets data security at its core. You sent over this research document, VVIP Hardware Exploration and Evalue.pdf, and we're going to break down those key insights on how specialized hardware is really pushing the boundaries of what's possible with next-generation cryptography.
Absolutely, yeah.
Yeah.
Sounds like you're looking for a clear and fast understanding of this complex field, and this document really nails a critical challenge. How do we move beyond the theoretical and make advanced encryption work in the real world, especially with all the increasing digital threats and, the looming presence of quantum computers on the horizon? We're going to help you find those aha moments.
Exactly. So today, we're really aiming to understand how crucial custom-designed hardware is in making technologies like fully homomorphic encryption, that's FHE, and post-quantum cryptography, or PQC, actually possible. We're going to explore the challenges they face and all the progress being made in this, this really vital area. Okay, so first things first. Why is there this urgent need for new types of cryptography in the first place?
Well, the document points to a big game changer that's coming: quantum computers. They have the potential to completely disrupt the public key encryption methods that are like the foundation of our digital world today, things like RSA and elliptic curve cryptography. And the reason is quantum algorithms could potentially solve incredibly quickly the math problems that these systems rely on for security, basically cracking them wide open.
So if quantum computers become powerful enough, a lot of our current encryption would just become completely useless. That's a pretty scary thought.
Yeah, it is. And that's where post-quantum cryptography comes in, PQC. Researchers are working on entirely new cryptographic methods based on mathematical problems that are thought to be really, really hard to solve, even for the most powerful quantum computers imaginable. The document lists a few promising candidates. You have lattice-based, multivariate, hash-based, isogeny-based, and code-based cryptography. All of these could be the building blocks of a post-quantum secure world.
Okay, so PQC is all about creating algorithms that can resist quantum computers. But what about homomorphic encryption, or HE, that we mentioned earlier? What problem is that trying to solve?
So HE comes at data security and privacy from a different but equally important angle. The document highlights the growing need for people to have more control over their personal data,
Hmm.
who can access it and how it's used. Homomorphic encryption offers a pretty revolutionary approach because it lets you perform calculations directly on data that's still encrypted. So your information can stay completely confidential, but you can still use services that need to process it in some way.
That sounds incredibly powerful. So, like, I could have my financial data analyzed by some service, but they wouldn't actually see my raw, unencrypted numbers.
Exactly. And here's where things get interesting. The document points out a fascinating link. While PQC and HE address different security and privacy needs, many of these advanced techniques, especially fully homomorphic encryption, the most versatile type of HE, and a lot of PQC schemes, actually share a common mathematical foundation called ring learning with errors, or RLWE. And that's a form of lattice-based cryptography. So there's this underlying synergy between them.
It's interesting how these seemingly different solutions have this common root. All right, so we understand why these new methods are important, but what are the challenges in actually using them in real-world applications? The document mentions some performance issues with current hardware.
Right. The document emphasizes that lattice-based algorithms, although very promising, run into performance bottlenecks on the hardware we have today. The math involved is just very demanding for our current systems.
I guess it makes sense that more complex math needs more processing power. What are the specific obstacles when it comes to fully homomorphic encryption?
The document points out several key challenges that are unique to FHE. First, the calculations in HE rely on modular arithmetic, but with incredibly large numbers. It's like doing arithmetic where after you reach a certain number, the modulus, you loop back around like a clock face.
Mm.
But this is way more complex than the standard integer math that our CPUs are designed for, and current hardware isn't good at handling these huge modular operations, especially with the large prime numbers that are often needed.
So our everyday computers just aren't built to do this kind of specialized math efficiently.
Exactly. Second, the document mentions that encrypting data with FHE makes the encrypted data much bigger. This is called ciphertext expansion. They mentioned that in some research, the data size increased by up to 50 times after encryption. Imagine encrypting a small file, and it turns into this huge, massive file. That's a big problem for data storage and transmission bandwidth.
50 times larger, that sounds like a logistical nightmare.
It definitely is. And finally, Actually performing computations on this encrypted data is incredibly demanding. It's not just a matter of encrypting the calculations you do on regular data. A lot of HE operations, like multiplication, require extra complex steps. The document specifically mentions the number theoretic transform, or NTT, as a prime example. These extra steps lead to a huge increase in the number of calculations, which means longer wait times for results, higher energy consumption, and problems with memory capacity.
So FHE has this amazing potential for privacy-preserving computation, but it's just too slow and resource-intensive to use widely with current hardware.
That's the core issue, yeah.
Yeah.
And that's exactly why the document highlights hardware acceleration as essential for making FHE practical, basically using custom designed chips that are specifically built for these tasks. Research has explored using FPGAs, ASICs, and even GPUs to speed up HE operations, and they've shown huge performance improvements compared to software-only solutions.
It makes sense. Specialized hardware that's tailored to these calculations could be a game changer. What about post-quantum cryptography? Are there similar hardware considerations there?
Absolutely. While the document focuses mainly on hardware for FHE, it does point out that the NIST standardization process for PQC considers not just the security of these algorithms, but also how well they perform and how easily they can be implemented in hardware. So even for PQC, having efficient hardware is really important for widespread adoption.
Okay, so specialized hardware is key for both FHE and PQC. The document then goes into exploring this hardware aspect, starting with what they call a bottom-up approach. What does that involve?
They explain that for FHE, their research took a bottom-up approach, starting with the modular multiplier. This is a fundamental building block because it's heavily used in core FHE operations like the number theoretic transform, the NTT, and polynomial multiplication. You can think of polynomials as a way to represent complex data in these systems.
So the idea is if you can make this basic math operation faster and more efficient in hardware, it will make the whole system faster.
Exactly. They did a thorough exploration of modular multipliers, looking at the trade-offs between throughput, how much data you can process per time unit, latency, the delay in getting a result, the physical space it takes up on the chip, and the power it consumes. They even looked at how the size of the modulus, those huge numbers we talked about, affects all of these factors.
What kinds of modular multiplier implementations did they look at?
They group them into two main categories. First, you have bit serial designs, which do calculations step by step, reusing the same hardware components multiple times. They talked about interleave multiplication and Montgomery multiplication as examples. And then there are bit parallel designs, which do the entire multiplication in one go, followed by a step to bring the result back within the modulus. Examples here are methods using Barrett reduction and also Montgomery reduction, which can be done both serially and in parallel. These different approaches basically represent different engineering trade-offs. Some prioritize speed by doing more calculations at once, while others try to save on hardware by doing things iteratively. The main point is they were very thorough in exploring which of these basic building blocks works best for the demanding requirements of advanced cryptography.
Okay, so there are different ways to do this core math operation, each with its own pros and cons in terms of speed, size, and power usage. The document mentions specific algorithms like interleaved radix 4, Montgomery iterative, Barrett, and Montgomery. What were some of the key takeaways from this exploration of modular multipliers?
One important finding was that a particular type called MONTMC, which is Montgomery multiplication with a modulus constraint, turned out to be the most efficient at this level. They found it offered the best balance of high throughput, efficient use of chip area, and low power consumption. This is a valuable finding for hardware designers because it suggests a preferred building block for future designs.
That sounds like a very useful insight for engineers. They also mention looking at how the area and power consumption of different multipliers, like Barrett and interleaved, are affected by the size of the modulus. What did they learn from that?
They broke down the area and power usage of these multipliers into their individual components, like the multipliers themselves, adders, subtractors, and registers that hold intermediate results. This let them see which parts were contributing the most to the overall area and power footprint. For example, in the Barrett multiplier, they saw that as the modulus size gets bigger, the three multipliers inside take up a larger and larger proportion of the total chip area. It makes sense because bigger numbers need bigger multipliers. They also looked at how the proportion of area and power used by combinational logic, the parts that do the actual calculations, versus sequential logic, the parts that store information like registers, changes with the modulus size. This gives them important insights into potential bottlenecks and areas for optimization.
The document also talks about accurate power measurement for ASIC modular multipliers using a tool called Primetime PX. Why was it so important to measure power so precisely?
Accurate power measurement is super important for making energy-efficient hardware, especially when power consumption is a major concern, like in mobile devices or embedded systems. Primetime PX lets them do a more detailed analysis of power over time in ASICs, taking into account how the transistors in the circuit are actually switching. This level of detail is much more accurate than just looking at average power and helps engineers find areas that use a lot of power so they can optimize the design for lower energy usage, which is essential for making these advanced cryptographic techniques practical.
And then there's this thing called the modulus counting function, or MCF. That sounds complicated. What was that all about?
So this was a new idea they introduced. In FHE, the modulus, that big number we wrap around with, needs to be a prime number. And often, hardware is designed to work with a maximum modulus size. The modulus counting function helps you estimate how many prime numbers there are within a certain range, given a particular constraint on their form. This constraint comes from the fixed size limitations of the hardware. It's like having a limited number of ingredients for a recipe. The MCF helps you figure out if you have enough of the right kinds of prime ingredients within the hardware's limitations to make the secure dish you need.
So because the hardware can only handle numbers up to a certain size, you're limited in the types of prime numbers you can use in FHE calculations.
Exactly. And the MCF becomes a tool for choosing the right constraints based on both the security you need for your FHE application and what the hardware can actually handle. For instance, if an application needs a certain number of different prime moduli for security, the MCF can tell you how big the constraint needs to be to ensure you have enough primes within the hardware's limitations. They even came up with a new mathematical formula to approximate this MCF and tested how accurate it is. This is a big step towards bridging the gap between the theoretical demands of FHE and the real-world limitations of hardware.
It sounds like a crucial tool for making FHE more practical. Okay, after this deep dive into multipliers, the research moves on to something called the ring processing unit, or RPU. What is that exactly?
The RPU is described as a custom-designed vector architecture that's specifically built to speed up those ring learning with errors, or RLWE workloads. These are at the heart of both FHE and PQC. Think of it as a specialized processor core made just for these complex calculations.
What are some of its key features that make it so good at this?
It has some really innovative features. Being a vector architecture means it can perform the same operation on multiple pieces of data at the same time, which is very efficient for many cryptographic algorithms. It has separate pipelines for getting data from memory, doing the calculations, and rearranging data, which they call shuffle. This parallel design makes it much faster than traditional processors for these parallel computations. The RPU also has a large, fast, local memory called a scratch pod for quickly accessing frequently used data, special vector registers for holding results, and crucially, it has built-in support for large word modular arithmetic, those big number calculations we talked about.
So it's not just running these algorithms on normal hardware, it's a processor designed specifically for FHE and PQC operations.
Exactly. They even created a simplified set of instructions for it, called B512, with only 17 core instructions. This helps minimize overhead and maximize efficiency for those specific tasks. The document details key components like the vector data memory, VDM, a high-performance large arithmetic word engine, HPLE, with the special arithmetic units, the vector register file, VRF, and fast connections called crossbars to move data between these components efficiently.
They also mentioned exploring different designs for the RPU, like changing the number of HPLEs and how the memory is organized. What did they learn from that?
They tested different RPU configurations, varying the number of those HPLE units and how the memory was divided. They found that having 128 HPLEs and 128 memory banks gave the best performance relative to the area it takes up on the chip when running the number theoretic transform, that key math operation for FHE and PQC.
That's a very specific and useful finding, and they confirmed this through simulations.
Yes, they implemented the design in a hardware description language called RTL and tested its performance. They also created a cycle-level simulator, which is a software model that mimics the hardware very precisely. This simulator was very accurate, around 97% compared to the real hardware, which gave them confidence in their design choices and performance predictions.
The document mentions a huge speed up with the RPU compared to a normal CPU when doing the NTT. How much faster was it?
The speedup was really impressive. For a 64K 128-bit NTT, they measured a speedup of about 1,485 times compared to a high-end 32-core AMD EPYC CPU. This really highlights the power of specialized hardware for these advanced algorithms. That kind of speedup could make things that were impossible before suddenly possible.
Wow, that's a massive difference. It really shows you can't just run these complex algorithms on any processor. They also did some tests to see how sensitive the RPU is to things like multiplier latency and memory access times. What did they find out?
These tests were important for understanding which parts of the hardware had the biggest impact on performance. For instance, they found that the RPU's performance wasn't really affected much by the speed of the multiplier, probably because the whole system is heavily pipelined, like an assembly line where different stages happen at the same time. But they did find that the initiation interval, which is how often you can start a new operation, had a bigger impact. They also analyzed the delays caused by shuffling data and moving it in and out of memory. They found that even though the NTT uses fewer load store instructions than shuffle instructions, the RPU was actually more sensitive to load store latency. This suggests that optimizing data movement could lead to even better performance. They even compared the RPU to theoretical limits based on memory bandwidth and found that memory access wasn't a major bottleneck in their tests.
That's really valuable information for both designing future hardware and optimizing the software that runs on it. Moving on, the research talks about a system called CoHEF-HEE. What's that all about?
CoFE stands for Coprocessor for Fully Homomorphic Encryption Execution. This is a system-level design, also implemented in RTL, that they actually turned into a physical chip specifically for accelerating the polynomial operations in FHE. So this goes beyond just simulations. They actually built a working chip.
Wow, they actually built a chip just for FHE. That's a big deal. What's the architecture like?
It includes these specialized processing elements, or PEs, that are designed for modular arithmetic and those butterfly operations we talked about, which are key for the NTT. It also has a dedicated multiplier data mover and controller, MDMC, to handle multiplications efficiently. Direct memory access, DMA, for fast data transfers, on-chip memories to hold the data, and even a small ARM Cortex-M0 processor to manage everything. It's a very complete system on a chip specifically for FHE.
It sounds like a purpose-built solution for FHE. What kinds of operations does it accelerate?
The document highlights that CoFE is designed to speed up ciphertext multiplication, which we've already discussed as one of the most computationally intensive operations in FHE. Making this faster is key to making FHE practical.
And how did it perform compared to running FHE software on a normal processor?
The results were pretty amazing. They compared CoFE to the Microsoft Seal library running on a high-end CPU for ciphertext multiplication with different polynomial degrees and modulus sizes. They found that CoFE was significantly faster and, in some cases, used 2 orders of magnitude less power for the same computation. That means it was like 100 times more power efficient. This suggests that some applications that were too power-hungry before might now be possible even on battery-powered devices, which opens up a lot of possibilities.
2 orders of magnitude. That's incredible. It shows how much better it can be to use custom hardware. They mentioned using a Barrett multiplier in CoFE. Why was that choice important?
They chose the Barrett multiplier because it was especially efficient for the types of modular arithmetic needed in their implementation. The document suggests that for their design goals and the specific numbers they were working with, the Barrett multiplier was the best option in terms of performance and resource usage.
So they really went deep into FHE hardware, from basic arithmetic units to a whole coprocessor. Now let's talk about post-quantum cryptography. It looks like they also did some hardware evaluations of PQC signature schemes.
Yeah, they did. They looked at how to implement several of the leading PQC signature schemes that were part of the NIST standardization process, which is the effort to find the next generation of quantum-resistant crypto standards. They used tools called high-level synthesis, or HLS, to implement these algorithms on both FPGAs and ASICs. HLS lets you write hardware designs in a higher-level language like C, and the tool converts it into a detailed hardware description. This makes the design process much faster than writing hardware code by hand.
Right, so HLS is like a more abstract way to design hardware, which makes it easier to experiment. And they applied a consistent design approach and the same set of optimizations to several candidates like dilithium, Falcon, Rainbow, Picnac, and Sphinxes, plus Bally's. This allowed them to compare them more directly.
Exactly. This standardized approach helped them test different designs and find performance bottlenecks in each algorithm. They described how they took the standard C code submitted to NIST and adapted it for HLS. This often involves big changes, like replacing standard library functions with hardware-friendly ones, managing memory differently, and being careful with pointers, because software code doesn't always translate well to hardware.
So you often need to translate and optimize the code to make it work well in hardware.
Yeah, that's right. And then they presented their results in terms of performance, like how fast it is, power consumption, and the area it takes up on the chip. They did this for key generation, and signature verification for each algorithm at different security levels and with different optimization techniques.
And what were some of the key differences they found between these PQC schemes?
They found some interesting things. For dilithium, a leading candidate, they found that a pipelined implementation often worked well in terms of both speed and resource usage. For Falcon, another lattice-based scheme, they noticed that the Falcon 512 parameter set was better for speed, and that using loop pipelining could make it even faster. For Rainbow, a multivariate approach, they found trade-offs between area and speed, depending on how they optimized it. They also thoroughly tested PI80, a zero-knowledge proof-based scheme, at different security levels and with different optimizations. And finally, they compared SCTSS8 plus SAA, a hash-based scheme, to its performance in software.
It sounds like each algorithm has its own unique hardware characteristics, so choosing the right one depends on the application and the hardware you have. And they implemented them on both FPGAs and ASICs.
Yes, they targeted an Arctic 7 FPGA, which is good for prototyping and testing, and also a 65mm ASIC technology, which is more for custom designs and mass production. This let them compare the speed and resource usage between these two types of hardware. They even explored optimizing some PQC operations for constant time execution, which helps protect against certain attacks, trying to achieve performance similar to handwritten hardware code.
That's a really thorough look at the hardware side of these PQC schemes. So, wrapping up this deep dive, what are the most important takeaways for our listeners?
The main takeaway is that specialized hardware, like the RPU and CoV-AC, can make a huge difference in speeding up the complex computations needed for both FHE and PQC. This is crucial for making these security technologies actually usable in the real world. Also, the research shows that HLS tools are becoming increasingly important and powerful for implementing complex algorithms in hardware quickly.
And why should our listeners care about this?
While understanding these hardware advancements is becoming more and more important as quantum computing becomes a bigger threat. The choices engineers make when designing hardware, balancing things like performance, size, and power consumption, have a direct impact on whether and how these advanced cryptographic techniques can be used in the devices and applications you might use in the future.
That makes a lot of sense. It's not just about clever algorithms. You need the right hardware to run them efficiently. So here's something to think about. With all this progress in hardware for FHE and PQC, what new applications do you think will become possible in the near future? And what new ways of thinking about security might emerge as a result? Maybe it's worth checking out the NIST PQC standardization process to see which algorithms are gaining traction and are likely to shape the future of digital security. Thanks for joining us for this deep dive.